Thank you. My name is Haijun Su from Ohio State. I have this is a set of lecture notes I used to give to one of graduate course. I have a few copies of my lecture notes. Feel free to take it. So I'm going to talk about some computational methods solving kinematics problems.
Too deep at the other side. Oh, it's too. Okay, keep closer.
Thank you. Okay, this is the outline of my presentation. We'll talk about classification of kinematics problems. Some of the topics, Professor McCarthy and Professor Kerr and Professor Kuski already give some some introduction to some of the method and kinematics problems. So we'll briefly go through those things. Then we'll talk about some mathematics preparation, mainly the terminology that we may use, and then we'll talk about the method for solving the system of polynomials. And really, the two major methods we talk about is one is resultant elimination approach. Second one is homotopy continuation approach. And then I will demonstrate the use of these two approaches to solving some kinematics problem. One of them is well known as inverse kinematics general 6R manipulator problem, and the other one is the forward kinematics of Stewart golf platform problem. The first method, I'm going to use the first method to talk about solve this problem, and then the second method to solve this problem. And last I will have some mathematical demonstration. I may not have time to answer those details to the mathematical notebook, but I have those the notebook, zipped into with this presentation, and you can download from the workshop website. Okay, so first of all, the kinematics problem, I can say there can be classified into two methods, two problems. One is for analysis. Second one, analysis, you have the mechanism, and you want to find the relationship between the input motion and output motion. So that's analysis problem. And the synthesis problem is finding the mechanism that can do the job. Okay, so that's Professor McCarthy already gave a really comprehensive introduction to the kinematic synthesis problem. So here's the one slide on how the kinematics of zero change, where the goal is to find in the position. Given the position orientation of the end-effector, finding the joint angle, that's the inverse kinematics problem. Eventually, you are here talking about you have this 6 joint axis, and you have the end-effector, which described using this homogeneous matrix. And your goal is to find this angle, theta 1 to 6. So that's called inverse kinematics problem. The forward kinematics problem is for the slow product form problem is finding you given these actuators, this 6 linear actuator, and you want to find the position orientation of the platform. So that's called forward kinematics problem. And then you have synthesis problem where you want to find a mechanism that can. This is a motion generation problem. You want to design mechanism so that the end-effector can reach as a given set of task positions. You end up solving polynomial equation like this. It's nothing more than just the distance between the 2 points equal to the r. So that's the kinematic synthesis problem. You'll find these dimensions of the linkage. Also, together with that, you can also find the joint parameters. Let's just do it now. The analysis. Then the kinetostatic analysis of compliant mechanism is similarly to that, where you have compliant, for instance, you have this parallel platform mechanism. You have this moving platform. This is very close to what Professor Busti yesterday gave the forward kinematics problem of the stool platform. Except here you have the limbs are now is a linear spring. Okay, you have the constant of the spring is given to you, and the problem is this: I have the platform and now I apply a given moment, force and moment, a general force and moment to the platform. The goal is to find where this platform can balance. That's the static problem. Well, actually, it's a couple of static and kinematics problem. Well, and more general version of this one, for spatial stool platform, is this: you have 6 limbs, but 6 limbs is all linear springs. Again, you apply a force and moment to the platform, and you want to find the equilibrium position or the tail of that effector. Okay, so that's the kinetostatic analysis of compliant mechanism. Well, you also have a synthesis, problem of compliant mechanism. Where here, this is an example of the problem. You have a compliant formal where you have this joint, which can be actually from, a pseudo-rigid body model of a compliant mechanism. And the goal is to, say, I want this end-effector or the coupler link pass through this, 3 tap positions. That's same as the kinematics synthesis problem. Well, also, then I add the constraints that this mechanism not only pass this 3 positions, but also has to satisfy some kind of static equilibrium conditions. So, for instance, you can design a bistable mechanism. Well, this position is stable position. This is at another stable equilibrium, and then you pass a unstable equilibrium position. And then you can formulate this also in a algebraic or polynomial equation form by doing some tricks. Okay, so that's the problem that we are going to go through. I will go through mainly the first 2. The compliant mechanism. I have a few slides showing how to formulate the problem, but the solution technique is the same. Okay. So at least a few slides on preparation of mathematics. So the first few, I think I'm going to skip this. You can read this, for univariate polynomial. Let's go to this multivariate polynomial system. So I have a polynomial system with n. In general, you could have a non-sphere polynomial system. You have n equations, but you have n unknown. So the monomial is really a product of the, exists in this form is part exploration of variables x2, xn, and alpha I are the degree of each variable in this monomial. The total degree of the monomial is the summation of the exponent of each of the parameter. The total degree of a polynomial is the maximum degree of all polynomials. And then the total degree of a polynomial system is really just product of the whole degree of each polynomial. So that's this. An example of this is here it's a quadratic. This is a cubic, and x1, x2 is a polynomial, which is a quadratic term. And you can find that this is a 6-degree polynomial system because this is 2 degree and this is 3 degree. So 2 times 3, that's 6. Okay. So yesterday, Professor McCarthy gave say, okay, this polynomial system has 10 to the power 46 degree. That's how you get you multiply this degree, you get the total degree. Okay. Now if you have you have 10 equations, each equation is a degree of 6. That's 10 to the power 6. That's how you get it. Okay. but actual number of solution is much less than its total degree. So and there is some method to count get a bound on the solution, number of solution for polynomial system. Okay. Homogeneous polynomials. You can say if the in a plain word, a polynomial is homogeneous if all the monomial has the same degree, then it's homogeneous. For instance, this is not this is homogeneous because every term has degree of 3, and this one is not. The homogeneous part of polynomial is the set of monomial is the highest degree of in the system. And then you have a non-homogeneous polynomial you can homogenize by introducing a homogeneous parameter variable. Okay. For instance, you can introduce, you can actually introduce, convert this xy by x1 divided by r, x2 divided by r. So and then you can convert this into a homogeneous variable. Now you have 3 variables, x1, x2, and r. So solution to homogeneous polynomial is this. If x1, x2 starts solution to the equation, and then the scale, the time the scalar is also a solution to homogeneous polynomial. So that has this feature. Here's some slide. One homogeneous, you have introduced one single homogeneous parameter. You can make it homogeneous. And M-homogeneous, you introduce M homogeneous parameter. Okay. For instance, this is 2 homogeneous homogenization. You can introduce 2 homogeneous values, R1 and R2. Okay. For 2 groups, x1, x2 is one group, x3, x4 is a group. And then introduce each parameter for each of the group. Okay. And then you can, you can define this as different variable, but you could, you may not necessarily. But this is how you homogenize. And the 2 homogeneous polynomial, the solution to that, if x1, x2, x3, x4 star is a solution to that, and any scaled of the first group and any scaled of the second variable group is also a solution to the solution homogeneous to the variable to the equations. So, and you can generalize to M homogeneous. Okay. Now we are interested in first, how many solutions are there in the polynomial system? Okay. It's not necessarily the total degree. And how can we obtain a solution to this problem, to our polynomial system? So, in general, this is a Bezout theorem. It says that a polynomial system has, it's just saying that the maximum possible number of solutions is the total degree. Okay, counting the multiplicities. Here's some example. I have two quadratic, so the solution set or the variety of the first one is a circle, the second one is elliptic, and if you want to find the common solution of these 2 polynomials, it's nothing more than just intersection point of these 2 varieties. Okay, and sometimes you get a higher dimensional solution because for instance, this polynomial system, you can see that x equal to 0 is really representing, not representing the isolated point, but actually it's a 9, x equal to 0, and y can be arbitrary. Okay? So sometimes you have the higher dimensional solution. But in most of the time, we are interested in isolated solution for the finite number of solutions, assuming that a polynomial system has a finite number of solutions. Okay, the example I have here. So I have a circle and then have a hyperbola. And the intersection here I have 4 in the second point. In some single case, you could have 2 single solution and 1 actually double solution. So the total count is 4. For some cases, you only have 2 real intersections, but 2 are in complex solutions. So example is here. And then we'll go on and let's think about this case. Think about what's the difference between this one and this one. This one, both are still quadratic. The first one is still a circle, but the second one is also a circle. So you can see that there are 2 solutions for this case, but we don't have 2 complex solutions. Okay. So the difference between these 2 is you have 2 real but 2 complex, but this one you only have 2 real, no complex. So and you can do a little bit, manipulation to these 2 equations. You subtract one from the other, you really get a linear equation. And then linear intersection of this 9 with the circle really only have 2. So the degree, you can see that the degree times these 2, 1 times 2, that's 2. So that's, the total degree of the system actually changes from 4 to 2. So you can see that sometimes the total degree give you a misleading concept. Okay. Now we get to the concept of solution at infinity. So in one, if you think about this homogeneous equation, this is 2 equations. Think about making it homogeneous. For this case, one homogeneous case. Now, think about now this homogeneous variable is very small, and then you can see if this is very small, I equal to 0, this is 0. So end up you're getting the homogeneous, the actual homogeneous part of the polynomial x squared plus y squared equal to 0, x squared plus y squared. So you can see that these 2 are identical, so they are solution to this homogeneous homogeneous equations. Actually, in fact, x times 1 plus I and 1 plus minus I, there are 2 solutions. So that's called solution at the infinity. Really, the solution at the infinity is actually the solution, non-zero solution of the homogeneous part of the original polynomial. Okay, that's in plain. That's something that easy for me to understand. So maybe not mathematically not that accurate. So, but helps me to understand for engineers. Okay. So now we worry about how we can find we find how fast we can find a solution. We also find how stable or is the solution process robust. Does it deal with singular cases? And also we worry about how many solutions are there in this polynomial system. Can we obtain all of them? Sometimes it's pretty helpful to find all of them. Why do we care finding all solutions? If I can find one, in some cases, it's maybe you just very happy with finding one of the solution. But using the iteration method, sometimes if you have multiple solutions, you may end up converge to a solution that you don't want. Then this technique will help you to find all the solutions and then result a knowledge about where the solutions are. So that's really a global solver. So that's when you will need this kind of solver. Okay. So here are the example of solution techniques. I don't mean to be comprehensive, but some of the solution process I'm aware of. Newton's method, you don't need you can find one solution, but you need a good initial guess to the solution. Interval method, there's no guarantee you can find all of them unless it exhausts all possible intervals. Algebraic solver, like group basis, and this Ritt-Wu method, which is actually a Chinese mathematician at this method, very much similar to me. It's similar to the group basis method. Elimination method is something that I work a lot on. So I used to work a lot on. So this method is, can give you a very fast solution, but it's not a general solution to most of kinematics problems. Most of the time, you end up have to using your experience and using to do a lot of trial and error finding the result and the matrix, which is a tedious and heuristic process. And the second one is more general. You don't have to, here if you will worry about, you want to find a solution fast, say you want an online solver. It has to be done in real time. Then this method can be useful because most of the work can be done offline, and then you hard code that formulation, and then the real-time online calculation is minimized. Homotopy solver can solve relatively large problems. It's easy to use parallel computation. So here a large problem, I'm thinking probably 10 to 15 polynomials, something like degree of million or tens of million can be solved using a modern HPT, high performance computer. Okay. So these two methods, we're going to focus on that. So that's just what I said. Let's focus on the first one. Okay. So the overview of resultant elimination method is this in this slide. This is the basics. Sorry that it's cut. Okay, so you have a system for monomial, n polynomials, and you can suppress one of variable. Okay, and then this third step is the key. Sometimes it's a general approach, sometimes you don't have. You generate actual polynomial, which contains the variety of original polynomial in this equation. So that means if z is a solution to the original polynomial, it also should vanish the actual polynomial. So, and that's how you can obtain those actual polynomials. Sometimes it's by experience, sometimes by geometric intuition of your mechanics system or your linkage system. So if I have find this actual polynomial, I can construct what's called resultant matrix, which typically a square matrix with a one suppressed variable in this, and it should vanish equal to 0 for a general solution, a non-solution. If Zn is a solution, it should vanish. The determinant should vanish. If it's for a general value of Zn, it should not vanish. That's a way to check if your resultant matrix is valid or not. Okay. And then once you have that, you're mostly done. Then you can program this matrix in your computer program software. And then this is what you will need. Okay. From here to the left is linear algebra, which you can convert this to a general eigenvalue problem, and you can use linear algebra to solve the rest of work. And the back substitution is also a linear process where you can really use the general eigenvector to solve the other variable instead of doing back substitution. So the key part is this step, and this is the step you have to validate your matrix. And once you have that, you are done. You are good to go. And how do you use it? You just use a random value for the suppressed variable, substitute and see if that determinant goes to 0 or not. Okay. And this is a probability 1 with a probability 1 of success. Okay. Means 100%. Okay. So let's do two example with how do you generate resultant matrix. For two polynomial, there's already something called Sylvester result, and we have two polynomial, what you can do is multiply the first polynomial by a list of monomial, say x, y is the suppressed variable. You want to eliminate x from these two equations. So what you can do is multiply the first equation by this list. So x, 1, the 1, x squared to x to n minus 1. So that's, you get m polynomials, right? So including the original one here. Okay. So you are generating actual polynomial in a systematic way. Okay. So you can see here, if y is a solution to this polynomial x1 and y, and it should vanish. Okay. So it's guaranteed the solution to the original polynomial system is in this actual polynomial. And similarly, you can do the second part by multiplying the second polynomial by this list. So you get another L equation, polynomials. So you construct this into this matrix, and this is the monomial set of the x, and this a, I, and bi is the function, is actually function of polynomial of the suppressed variable y. Okay. Then you do checking if this is valid by substituting a random variable to a y and make sure it's not singular. Okay. So that's the second approach is called Dixon's resultant. That's for n polynomials. If we have n, this is a general case. You introduce a new variable called alpha n, alpha to alpha n. So then you calculate this determinant by the first row is nothing nothing more than just the original equation, but with xn suppressed. Okay. Now the second row is replacing the first row by just substituting x1 by alpha 1. And the third row is nothing more than substituting x2 by alpha 2 for the second row. And the last row is just this, where xi is substituted by alpha I. So you can see that if I calculate the determinant of this matrix, I can always have the factor of xi minus alpha I. And you can see why is that, because if I substitute x by alpha I get the first row and the second row will be the same. If a matrix have two identical rows, it's singular, the determinant is equal to 0. That says that this determinant is guaranteed to have this factor. So let's factor out by dividing those, factor out those factors. So let's divide those factors. So I get a polynomial with a variable of xi and alpha I. Okay. Now you can see here, if x is, x here is the vector of x to x n minus 1, is a solution to the original equation. That means it satisfies, it make this all vanish. Okay, now if a matrix with one row all vanish to be 0, that means the determinant has to be 0 for any arbitrary value of alpha I. Okay, now this is a polynomial. Okay, now you can see that this polynomial in terms is a polynomial with in the variable of alpha to alpha n minus 1. But then it vanishes for a solution to the original equation for any arbitrary value of alpha. Okay, doesn't matter what alpha it is. So that means the coefficient. If a polynomial is always vanished for for any arbitrary value of the variable alpha I, then I can say the coefficient of that polynomial has equal to 0. Okay. So if I make that, I get a bunch of extra polynomial. Okay, in terms of the x to xi minus 1. So that's how you construct extra polynomial using resultant using Dixon's approach. Now this is a general, and you can obtain a a matrix form of xn, so you get a matrix, and you can calculate the determinant of the matrix, so you can get a univariate polynomial in terms of xn, and you can check, by that's the same as other methods. You can, by checking if this resultant matrix is valid or not by just substitute a arbitrary value of just random value to that and see if that's non-trivial. If it's non-trivial, then you are done. You are good to go. Okay. But in a lot of cases, in kinematics problem, the equations have a lot of zeros, have a lot of missing terms, missing monomials, so you end up will often get a singular one. So then you have trouble. So then you have to find other way to generate extra polynomials. Here's the slide, how you convert, in general, I have a resultant matrix, how you convert to a general eigenvalue problem and solve them using linear algebra. So that's a step. This is called companion matrix of the matrix polynomial. Okay, and you can find the generalized eigenvalue of this system. Okay, where A1, A2 is written as this. Well, if one of them is singular, there's another way to treat that. Here I have a demo. Actually, I have two polynomials. Both are quadratic. I demonstrate how to. So basically, I have two polynomials here. So this is how I do it in Mathematica. So here's the example how in Mathematica there's a built-in function called resultant that you can do for two polynomial case. But I show you a manual way to do it. I have two equations and then you multiply the first one by 1, because one of the equations is in is linear in this in the variable of y. So that's why you multiply by F1, and the second one, F1 times F, just see the self, and the second one is F1 times X, and then you get 3 polynomials. So actually, for this case, you only get one extra polynomial, which is P2, by multiplying F1 by X. So now you get 3 polynomials, P1, P2, and P3, and it happens to be you have 3 monomials in terms of X. You have X, 0, really 1, X, and X squared. So you can write it in matrix form. This is the resultant matrix. And the determinant of that resultant matrix, you can get this, and you can solve this. So there's a built-in function which is called resultant, and that's you get the same solution. Okay. And the Dixon resultant is doing this. You do the determinant by substituting F1 by X by alpha, and X2 also X by alpha. So you get the determinant, and then you get the delta, and then you find the coefficient of delta in terms of the variable alpha. For this case, we only have one alpha, so you get a 2 by 2 matrix. You see, usually this Dixon resultant give you a smaller matrix. Here, for this case, we have 2 by 2. You get the same result, and you can take the determinant, and you can get the solution. Okay. So you can take a look at the note. So now let's talk about the homotopy approach. That's the first approach. Homotopy approach is a global solver, polynomial solver. So here you have a target system you want to solve. This is your polynomial system you want to solve. Now you want to construct the second called start polynomial. The start polynomial system, you have the known solution to that start system. So that's the tricky part, to construct a good start system. And then you define the homotopy function by this. Here if lambda equal to 0, it's starting from the target, the start system. And then you varying lambda until lambda equal to 1, you get the homotopy function is just the target system. Okay. So the process is this: if you know the solution to the start system, so each of these points is a known solution to the start system. Okay. Now at lambda equal to 0, now you're varying lambda slightly. Okay. Now, because the polynomial system is continuous, the function is continuous, so the solution to the polynomials also is continuous. So at any step, increment of lambda, you can solve the homotopy function for an update of your solution. Okay. Once you get updated, you keep continue through the path. This is called homotopy path tracking until you get to the point lambda equal to 1. If you reach lambda equal to 1, you really get a solution to the polynomial system. And sometimes it does not, get to the lambda equal to 1, and you cannot continue. That's a divergent path, so that's the path that we just discussed, those paths. And each of the tracking process is nothing more than solving linear equations using iteration approach. That's the basic principle. Here I have an example how you do it. This is the quadratic equation. You have original equation x squared plus 3x minus 4. And the start system, let's say I have x. I want to solve the solution, find a solution of this polynomial system. Now I do construct a start system, x squared minus 4. So I know the solution to the start system, which is plus minus 2. Okay. Now I want to find this solution. So what I do, I construct a continuous function or a homotopy function by introducing a variable t for this case. The t varies from 0 to 1. Okay? And t equal to 0 is the solution of the start system. I have plus 2 and minus 2 here. Now I increment the t slightly. I then solve the updated equations. I track the solution. I get to this solution. Okay? I can increment the solution until I get to the t equal to 1. I get the solution of the original target system. Okay, that's how it works. And for each of solution in the start system, you get one homotopy tracking. So the number of homotopy tracking, homotopy paths to be tracked is equal to the number of solution of the start system. So if your start system is efficient, that means the root count of your start system is as small as possible. You are minimizing the number of paths to be tracked, meaning you are speeding up the computation. Okay. The start system, there are a list of ways to, there are some requirements for start system. First of all, you have to know the solution to the start system. Second, the monomial set needs to be, the maximum degree needs to be a superset of the target system. So meaning the maximum degree, if you have a cubic equation, you cannot use a quadratic equation to check at the start system, because the two quadratic equations only have two solutions. You can't converge. You can't check to the third one. So you can see a number of solutions of the start system have to be bigger than number of solutions in the target system. And this is the way to construct start. Also, how you count the root of the start system. One homogeneous, two homogeneous, and the partition linear product. And this is have an increasing generality, meaning the number of root count is decreasing from top to down. This is the total degree for a star system, and this is the parameter homotopy, which you mean you already solved a system once, and you don't solve the same system, but just the coefficient are different. You can just use the solution of the polynomial system you just solved, and then you only end up checking the exact number of solutions. You are not wasting any of time in the tracking solution that do not give you the yes.
Excuse me, on the choice of the start function, for example, if the target function has like a real solution, but start function you start with something with a complex number solution, do they converge, or is there any more condition on the, because my concern is like if the target function has like real solution, but the initial guess has the initial start function has the complex solution. Yeah. So how
in the homotopy method, the software all written in the field of complex field. Even you are for engineer, you're only interested in the real solutions, but the coefficient is assumed to be complex. All the start system, when it's randomly generated, the coefficient of the star system or randomly generated complex numbers. So you're working on the complex field. So your star system is not necessarily a real solution. It's actually complex in general. I show you the software that you can download from there. It's actually it's randomly generated complex polynomials. Yes.
How do we know that the trajectory tracked by any of these solutions is continuous? There are breaks in between.
Say that again?
How do we know that the trajectories that these solutions follow, that these trajectories are continuous?
How do I know it's continuous? If you Well, actually, this is probably a the version. In the real thing, they some of software that they make it homogeneous, and then you're checking that if that homogeneous variable goes to 0, and that's meaning the solution goes to infinity. That's the solution you want to discover. Okay, actually, I have this probably give you some misleading information. Just help me. This is a solution that you want to discover. You don't want it. So actually, the software, if you find that homogeneous parameter goes to 0, you get a solution to infinity, which you don't want it. So, but in computationally, there are some more details in there. But I'll talk about how to use the software and understanding the result, interpret the result in a more practical way. Okay. Okay. Here's some example of how the star system. The first one is one homogeneous star system where really you take the total degree. The first polynomial has a degree of d1, so you're just using this, and then this is probably the simplest way. And this first loop has d1 loops, and the second one has d2 loops. So number of loops will be the product of all the product of d1 to di. Okay. The two homogeneous star system. This is actually for the 6R manipulator problem, so newest kinematic problem. And the star system, this is actually the solution. This is the star system. The original equation is more complicated than that. So this is an example of two homogeneous. You divide this the variable group into two groups. We'll talk about that in a minute. How do you count the M-homogeneous root count? Here's the way. So first, here's the step. First you divide all variable in M groups, and you denote beta j as the group of variable M groups of variable. And then dij to be the degree of each equation of I with respect to the variable in J's group. And then you calculate this product, and the root count of all M-homogeneous real number is just coefficient of this term in this polynomial. I give you an example here. This is the 6R inverse kinematic problem, which is I get from this Nolan Tsai's book. So this is a polynomial. It looks like AI, these are coefficients, just not numbers, and then x1, x to 8 are the variable to be solved. So for this case, you have it's two homogeneous case. So you divide this into two groups, x1, x2, x5, x6, and x3, x4, x7, and 8. These two groups. So using this this slide, you can find the real number. You can estimate how many root counts are there in the star system. So finding dij, for instance, the first equation here, you have 4. So the first 4 actually it's identical. So this polynomial is linear in this group. You can see that there's no mixed term of this. There's no quadratic term, square term of this variable, and there's no mixed term. Meaning there's no x1 times x2. So you can see that the structure as this. So the degree of this polynomial in terms of this group is 1 plus 1, 1 here. And then you can do similarly. So that's the so the first 4 is the same. Okay, so it's identical structure. Now the fifth one is this x squared, x1 squared plus x2 squared. So what's the degree of this polynomial in this group? And how do I define the degree of a polynomial in terms of? So let's think about it. So x1, x2, x1 squared, x2 squared. So what is the degree of this polynomial? in 2. So, but in 2, is this with respect to this group, meaning if I only consider these are the variables, then the degree of this polynomial is 2. So how about the degree of this polynomial in terms of this polynomial, these variables? 0. So I don't have any term in those. So this is 2, 0, and 6 has x3 and x4, so which meaning I have 0, 2, and the 7th one is 5 and 6, that's 2, 0, 7 and 8, so 0, 2. So I get this, and then I calculate this, which is nothing more than so that's just so D1, that's beta 1. So because I have 4 of them, it's exactly the same. So, and then I have times, so that's product, so times 2 B1 square, because I have 1 here, 1 here. So that's 2 times beta I. So 2 times beta 1, because I have 2 of them, so that's square. And for this one, I also have 2 of them, so I read times 2 of B2 squared. Oh, actually, I'm using beta. Okay. So this is a 2 homogeneous, you have 2 betas. Okay. So the coefficient of the term of beta 1, the fourth, beta 2 to the fourth, is going to be, this is a polynomial. So finding the coefficient of this, you can think about, so what's the coefficient of this polynomial of this term? Well, the reason I take 4 is because I have 4 variables in this group, the 4 variables in this group. Remember, the k is the trump of term in the variable group j. Okay. So, I'm going to guess. So here I have beta 1 square, beta 2 square. Oh, here I only need to take the term of beta 1 square and beta 2 square. Right? So what's the coefficient of beta 1 square, beta 2 square? So well, you can do the exercise. You know, actually it's 96. So that's the original polynomials to be solved. The total degree is 256, but the 2 homogeneous polynomial is 96. Meaning if you're using 2 homogeneous Start System, you only need to check 296 paths. And in this 96 paths, you have 64 solutions in infinity, and then you have end up obtaining 32 solutions, and 16 of that solution are significant. So that's the example. I have a few more examples. So that's a synthesis problem that I worked on. So it's not it's a SS chain or TS chain. So you get this 7 polynomial equations, actually 7 quadratic equations. Okay. You can subtract one from the other to eliminate one of the variable r squared. So you can eliminate one variable by subtract one from the other. So you get 6 equations in here. Okay. And the 6 equations have the monomial list in this way, where the unknowns will be b. B has a coordinates of u, v, and w, and these are all vectors, and I have here really is dot product, okay, and square really the vector square is really just p1 dot itself. It's dot, like p1 dot p1, okay. So don't be confused by that. So if you take a look at this equation, so it's by doing this manipulation, you can eliminate all the square terms, and your monomial next looks like this. You the xyz, in terms of xyz, is a linear in xyz, but it's a quadratic. They are mixed in terms of them, u and uv w and xyz. So these are the monomials. So the GLP structure will be like this. Okay, you have actually the six of identical structure. The Start system will be just a product of two linear systems, which one is the UXYZ, the other one is UV and W. And this AIJ and BIJ are randomly chosen complex coefficients. Okay? And you can count how many roots are there in this linear system. That determines how many homotopy pairs to be tracked in homotopy solver. Okay, and you can see, here, I can pick any of this, any one of the linear factor for each equation, and then assemble a linear system. Okay, the linear product method, you can pick one linear product for each each polynomial in the Start system and construct a square linear equations, linear systems. And then the solution to that linear system gives you the solution, one solution of the Start system. Okay. Now the number of counts, root count in the Start system will be all possible combinations of the linear product. However, some of the cases it's not permissible. For instance, I give you an example. I pick, let's say I pick 4 linear product of for the first 4 equations of x, y, z. I only pick 2 for the last. Pick these 2 linear factor for the last 2 equations, and there's no solution to the system because it's first of all. The first 4 for randomly generated coefficients, I have 3 unknowns to solve, but I have 4 linear equations. It's over-constrained, so there's no solution. So it looks like you have 2 to the power of 6. It looks like you have 64 possible combinations, but not all of them are permissible. Okay, meaning you don't get a solution to the linear system. It's not a valid solution. Valid solution to the Start system. So, well, eventually, actually, you have only from this 6 equation, you pick 3 linear factors for x, y, and z, and 3 linear factors for u and w. So 6 choose 3, that gives you a possible 20 combinations. That means if I use a GLP Start, this is a general linear product Start system, I only need to check 20 paths instead of 64. So actually, this system is exactly 20, so I get the exact root count. So that's the best case. You're not wasting any time tracking solution that you want. Okay. And these are 2 possible combinations. Well, I have one here. I'm going to skip this. So this is 6R problem. Well, here if you take a look at these 2 equations, these are the linear product. I skip the constant part. Really, it's a linear combination of these variables. times the coefficient of the random driven. So this product two linear factors, and these four is just nothing more than this, and you can count how many possible combinations are there. In general you have two. Pick any one of them. It looks like you have 2 to the power of 8, but in this case, it's also 96, which is the same as the 2 homogeneous loop count. So it's nothing more than better than 2 homogeneous star system. But in many times, the GLB star system gives you a better or sharper root count to the polynomial system. Okay. Here I'm gonna briefly show a few slides on my research on compliant mechanism. The Kiddo's analysis of compliant mechanism problem. Here you have the platform problem where you are given. So I did mention this in the beginning. You have a platform, but these are the screens. You apply a given force and moment to the platform, and the goal is finding the equilibrium configuration of the platform. Now, the way to set up the equation is this: the distance constraint will be the distance from A to B is equal to Li, so that gives you 3 kinematic equations. Then you add in this static equilibrium equations, which you can use in a lot of methods. You can use in different approach to finding the equilibrium equation. You basically have 3 kinematic equations and 3 static equations. You want to solve them simultaneously to find the solution of the movement period as well as the deformation of the limbs. Okay. For the Kineto analysis problem, it's usually more complicated than the pure kinematic part because you have actual equations, you have actual unknowns, the deformation unknown also. So this is the polynomial system. Looks like you check the sine, cosine as independent variable. You have you can define the new variables, and so really you end up solving the 10 constraint equations and 10 unknowns. Show this here. And the GLP start system for this polynomial system, well, this is the best I can think of. It's based mostly because it's derived, because the equation are derived using vector algebra. So a lot of time you can find the linear product or the start system by observing the structure of polynomial. So for instance, this one is just CS squared, so because there's no mixed intent let's put that as an easy one. These are rho I and Li also variable because you remember the length of the links is also variables. The total degree of this polynomial system is 1,536. You can count the degrees by multiplying the degree of each polynomial, and then you can get. But this GLP starts to give you a number of 466, which is more complicated to count manually. Okay, have an example, a numeric example. You can find all the solutions, actually, the homotopy. This is a very special and symmetric case. You find the solution, and actually you are finding some bistable compliant mechanism here. Okay. These are the minimum energy is representing the stable equilibrium conditions. This is another solutions. Some are unstable. Many of them are unstable. This is a very symmetric case to show you that we probably you can figure out, by intuition, but it's nice if you have a computer tool that you can find all the possible configurations, and then make, see if that makes sense to you. Here's another example with a tri-stable compliant matrix with 3 minimum energy solutions. Here's another problem that we solved. It's called General 6-6 platform problem. This is probably the most complicated problem we solved. So we have the platform, but each link is a linear springs. And when you apply a force moment to the platform, so the equilibrium position needs to be found. So the Start System, we derive kinematic equations, we derive the equilibrium equations. So you have 7 kinematic equations, which are here, and then 6 static equilibrium equations. This is the kinematic equation. These 2 are equilibrium equations. Each of them is a vector equation, so each one is 3 actually. So 3, that's 6. This is 5 plus this 2, that's we get 13 equations. The total degree is about almost 5 million case. But if you're using software called Bertini, you can you end up tracking 253,000 tests and obtain 29,000 non-singular solutions. Now I want to show how we can use the result elimination approach and homotopy approach to solve 2 classical problems. The first problem is the well-known inverse kinematic of general 6R manipulator problem. The solution is actually from the first reference, the Ross solution. So a number of years ago, I actually wrote a mathematical notebook to follow the solution process, and I used to have it, use it as a project problem or project problem to graduate student, and then follow the process and you repeat the process, then you understand the solution, elimination approach process. So the problem is I have a general manipulator. So these alpha D's are all general. There's no 0 or 90 degree that make it convenient, like this Kumar robot you can solve closed form because you have a risk center, which you can decouple the first 3 and the third. In general case, you don't have that convenience. So how can we solve this problem? So the way we formulate the problem, you derive the forward kinematic problem. So these are a bunch of homogeneous matrices, or product of homogeneous matrices. Now, so this is the solution. The process, the overview is this in this slide. The first of all, you derive the forward kinematics equation. Then you split the equation by moving some of the matrices to the other side. The right side is T is given to you. So multiply some of the matrices to the right-hand side, so you can balance the equation and reduce the number of the total degree. Okay. So for instance, we can split. So the left-hand side we leave 3, 4, and 5. That's the way how they came up. And then the right-hand side we say have 1, 2, and 6. So you can balance the degree. Okay, that's the first step. Now the third step is to, let's say, only needed the third row and third column and third column, fourth column. Okay, so remember, this is left hand side, this is right hand side, so you have to make them equal to each other to obtain equations. Okay, so for instance, F13 should equal to G13. So that's give you an equation. Okay. So here we only need to work on the third column and fourth column, just because you notice here in the third column and fourth column, the right hand side you don't have theta 6, and you can think about why you don't have theta 6. Theta 6 only in the first two columns, and that's because you think about the last joint. Think about last joint. The last joint rotation does not affect the translation orientation of this point of this coordinate system. Okay, so and because we define the matrices in terms of Delaunay-Hardenberg notation, so the z-axis is assumed to be the rotation axis direction. So the last column is really the z-axis. The third column is the z-axis. The z-axis is not affected by the theta 6, and the origin also is not affected by the theta 6. That's why you don't have the. So you can see that I really already eliminated one variable theta 6. So end up I only have theta 1, 2, and 4 and 5, 3, 4, and 5. So here I should have 5 independent equations because I have 3 for position that's independent to each other. And then this third column, because it's a rotation matrix, so the last column of the rotation matrix has to be, the magnitude has to be equal to 0. Really, I have 3 equations, but 2 of them are independent. But we're going to use both of them to generate, all 3 of them to generate extra polynomial to eliminate variables. Now, what we do is, we want to eliminate theta 1, 2 from this 6 equations, actually, A and B. Okay. What we do, we treat sine, cosine of this variable, also the next term, as independent variable. Okay. So we have S1, S2 as one variable, S1, S3 as one. So these are the monomials set. We have 9 monomials in these 6 equations. Then we can generate more equations. That's the key step. And that's they generated 14 extra equations. Well, 80 are actually original. There are 80 more equations obtained in this way. It's called A dot B, B dot B, A cross B. But how they find out this? It's sort of kind of magic, but it's a lot of trial and error approach. It's called heuristic method, to construct polynomial equations. But there are some geometrical meaning for this equation. For instance, A dot B is really the A is the z-axis, and B is the origin from origin of this coordinate system to origin of the global system to the origin of the fixed joint axis. So you can see that. So if you do the dot product, is a vector project to the z-axis of this vector, and you can. So there's some geometrical meaning for that. Then you can choose this 14. You can choose 8 of them to construct a linear system to solve this, because here I only have 9 monomials. When I do this, I don't introduce extra monomial, but I have more equation polynomial, but I don't have new monomial introduced into this list. So that's actually important. You generate more polynomial, but then you have new monomial set introduced to the polynomial system. Then you have to keep increasing the size of resultant matrix, and you may have to may not or may not obtain a square resultant matrix. So if you pick 8 of them, and you can solve this because you have 9, well, excluding this one, so you have 8, so you can solve a linear equation to eliminate theta 1 and theta 2. And then the next step is using another step of resultant method to eliminate 4 and 5 by using the half tangent angle. The T3, 4, 5 is half tangent of theta 3, 4, and 5. And then the rest of is back substitution. The process, these details are here. So this is the third and fourth column. So like this, no theta 6 here. And then if you denote this A and B this way, okay. So you construct this 14 scalars. So you can pick 14. These are the 14. So you can the details are here, and you can read here. Then you can construct the resultant matrix to eliminate these monomials. Okay. Well, here the B are just numerical. There is no variable in B matrix. But however, I do have matrix variable in this, so I do a linear reduction to the polynomial system. So I have total of 14. I use 8 of them to eliminate, substitute the solution of these monomials. To the rest of 6, I should get 6 equations. So here I have 14, right? I pick 8. Or I can do a linear reduction. I just need to eliminate these monomials. So I get a set of polynomial in terms of variables of theta 3, 4, and 5. Okay, only I just use a linear algebra without any symbolic operation, for this. So now the next step is to eliminate the 4 and 5 to obtain a single equation with only invariable theta 3 only. That's another step of resultant matrix process. So what do? You have these monomials. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 9 monomial, including the constant. Okay. So now you want to eliminate this now, but you can multiply this 6 matrix by t. First, we will transform this 6 equation into using the half tangent angle formulation. So really, you have still 6 by 9 matrix, but this is the monomial set to be eliminated. So you are multiplying the 6 equation by T4. So this is a method, a typical method to generate an extra polynomial. You multiply the original equation by a variable. So you automatically get another 6 set of equations. So now you have 12 equations. When you multiply, you actually introduce more monomials to the system. So that's why you have extra polynomial. But here, the union of these two sets actually exactly give you 12 monomials. So you obtain a 12 by 12 monomial in this form. So you get a resultant matrix, a square resultant matrix. And at this point, you can see here the coefficient of this E's are all just a quadratic polynomial of T3. So you get a 12 by 12 matrix. Each element is a quadratic equation. Okay. So now either you can use take the determinant of the matrix and obtain a single valid, a univariate polynomial and obtain solution, or you can convert into using the method that I just mentioned, using this, convert this into a general eigenvalue problem, so using linear algebra to solve the equations. So then you do the back substitution, which is pretty, or you can use in general eigenvector. I will show you the mathematical notebook that using general eigenvalue and eigenvector method to solve the rest of problem. Okay. We have a demo here. Sometimes we have a few more minutes. I'm going to quickly go through. Okay, so this is this mathematical notebook that you can go through when you get back. So now here I define the Denham-Hartenberg, and then I define the forward. Actually define the forward kinematics, and then I formulate, the left and right equation. So left and right, you have 3, 4, 5. Right, you have 2. 3, 4, 5, and then 1, 2, and 6. Yeah. So this is just a constant. So that's x. That's a constant. So theta 1, 2, theta 6, and then you transform this into algebraic equation. So it's mathematical. You have to replace this using psi C1 and S1 and things like that. I can manipulate matrix. So I then have this left and right, and then what I have the force. So A and B, these are the fourth and the third column. A and B, and have left and right, okay? Then I have to simplify a little bit by cancel the square term. So the 16 equation, 14 equation are here. The first one is A dot B, and B dot B, and A cross B. This you can actually get 3. This you get 1 is a scalar. And this is another vector equation. So 6, 6, 1, 3, 6, 1, 1, that's 8 plus original 6. So you get 14. So you get equations, all the equations. And you can eliminate theta 1 and theta 2 by pick any 8 of them. Okay. And then you follow the steps. Let's see. Yeah. This step is actually obtain 6 equations from here. So you right now it's linear algebra. You eliminate theta 1 and 2, and then the next step is to eliminate 3 and 4 and 5. Okay. So now here this step is to converting using the half tangent of formula to replace the sine and cosine, so you get this. Okay. I think I will have more time to go over this, the mathematical notebook, but you can take a look at that. If you have any question, you can contact me. Few more slides. That's on the homotopy problem. That's the forward kinematic of Stewart problem using homotopy approach. And so this is the kinematic equation to be solved. It's nothing more than that, if I define this M using either rotation or homogeneous matrices, and then the constraint equation comes from the distance between A and B should be equal to L, and I should get 6 equations, and the unknown will be the matrix, okay? Meaning you have this variable and these variables. So because this is a rotation matrix, I have 6 extra equations because you have satisfied the rotation matrix requirement. So you have 12 unknowns actually, 9 here, 3 here, 12 unknowns, 12 equations, 6 equations here, 6 equations here. So that's the equation you want to solve. So if you're using, you can count the roots, number of roots. The general linear product, the total degree is 4,096. So you have 12 quadratic equations. So the 4,096. And the GLP Start System of this is 1,080. So you can, using the GLP Start, you check 1,080 paths. But here's another thing I want to mention. Yesterday, Jeff and Manfred actually gave an introduction to quaternion. So I'm going to skip all of this. In mathematics, you have a quaternion operation package. This is the operations. But I can show you that actually this is from the Charles Longford's paper. So using the quaternion, dual quaternion formulation, you can reduce the complexity of problem significantly. That's another advantage of using quaternion in formulating the kinematic problem. You see that the complexity of the problem is have the comparison of how you do it in matrix equation and how you do it in quaternion form. You can see that now I'm going to eliminate because the main reason is that I don't have to use the 6 extra constraint equations. I only need a dual quaternion. I only have 2 extra, so that's immediately reduce the number of equations in the formulation. The details I'm not going to go through. So, but you end up have 286. This is the total degree 2 to the power 8. That's 256. You actually give you 80 roots, and you can actually cut down by half. You can actually 6 roots are actually in pairs. So let me in the last few minutes just go over another mathematical notebook. I don't know why sometimes keep not projecting what I have here. So this is the note that if I followed the OnePlus paper to formulate a Stewart platform problem using homotopy solver to find the solutions. But to help you to use, and this is the software I use called PHC. The reason I'm using that is because it has a Windows application, and you don't have to do any installation. You just run this from command line of Windows. So to help you to generate a data file for PHC, I did wrote some interface that you can convert a mathematical equation into a text file and then run the PHC. So actually, I have a function called solve PHC, actually directly call PHC from Mathematica and find the solution. So the example here, I have the Stewart platform problem and formulate problem exactly I presented in the lecture notes. Have the using quaternion to formulate the problem, and this is the equation obtained. So I end up solving 8 equations and 8 unknowns. And then what I do is I call this equation I set, I solve this equation by PHC. The solution will save to that file. And you should make sure there's a command. This is the one that I can't post it on the website because it's an executable file, so you have to download from the website. Let me know if you have any trouble. But the solution file of the solver looks like this. It actually does give you try different start system and finding the best start system for you. It's quite automatic. So this is the beginning is actually the solution to the start system. You can see that it's a random generated complex number. So, and actually, if you go to the end of this, it has the statistic of all the solutions. You can see that we get 8 solutions in 40 pairs. So we all know that we have 40 solutions in this problem. I think over a few minutes, 10 minutes. Okay, I'm going to stop there here. Any question? I stop at 10:30, right?
Good.
All right, thank you. If you have any questions, you can always send me an email.
We'll take a short break and start up. Break probably close to 11.